Today we're going to learn about two different things that are very, very closely related: diffraction and resolution. Diffraction is related to interference, which we learned in SL, but we're going to review now, just to make sure that you guys are on board. And then resolution is just like an afterthought after diffraction. The idea is that once you know enough about this, you can use this to figure out how things are resolved, for example, in a camera, whether you can separate 2 points that are very far away or not. The first thing that we're going to discuss is interference. Now imagine that we have two waves that are exactly equal, so, put them one next to the other, they're perfectly like the same. And now these two waves are in the same position in space. So this means that the perturbation at each point actually adds up, so that I get a wave that's actually the sum of these two. This is called constructive interference, and we did that last year. However, we could have a different situation, right? So, for example, we could have this wave, and now I'm going to duplicate it, perfect. And this one could be right here. Now, if it was right here, what would happen is that these 2 points would add up to 0. These 2 points are in opposite places that would add up to 0. This would also add up to 0. So the result of these two waves put together would give us this, something that's flat. That is, the two waves would destroy each other. And that's why we call this destructive interference, because the two waves destroy each other. Now, when does this happen? Well, this happens when the phase difference, the difference the path difference, the difference between this point and this point is a certain amount. And what we can do is just look at this wave. So this is a whole wavelength. This is half of a wavelength, and that's exactly the difference between this wave and this wave. So we can deduce that when the path difference is half a wavelength, then we're going to have destructive interference. Now, this doesn't only have to happen for half a wavelength. For example, I could move this here and I would still have destructive interference, and in this case I would have 1, 2, 3 halves of a wavelength. So I could have 3 lambda over 2, and I could keep doing this. I could keep moving this over here, and then I would have 1, 2, 3, so wait, 1, 2, 3, 4, 5, and so on. So you probably see the pattern here, that for any odd number multiplied by lambda halves, I will have destructive interference. And remember that the way we normally express this is that when the path difference is 2n plus 1 lambda halves, then we have destructive interference. And this will come in handy. Actually, we will only need this result when we analyze diffraction. Diffraction is just like interference, but on a large scale. Okay, so imagine that I have a wave that's coming in here, it's flat, and then once it comes over here, we know that if this width is more or less the size of a wavelength, this is going to bend like this, right? Now for this we're going to use the Huygens principle, which says that each point in the wave acts as a little wave source. So actually what really happens is that this point does this, this point does this, this point does this, and then at each point here, all these waves add up using interference, and that's how we get the wavefront, which is normally something like this. But what we're interested in knowing is what's going to happen here at this screen. So at this screen, for example, at this point, we will have waves coming from here, 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 and all these little waves are going to add up here and using interference. What could happen here is that most of them interfere constructively, and then we will have a bright spot here if this is light, for example, or it could happen that they interfere destructively, and then we will have a dark spot here. But what we want to know is where the dark spots are located, because if we know where the dark spots are located, we know that the bright spot has to be between, right? So this basically means that we have to add up every single wave in here, but of course there's an infinite number of waves, so that doesn't seem very practical. So we're going to have to do a little hack in order to add these all up And also we're going to have to use some approximation in order to not get bogged down in the mathematics, which otherwise would be very, very complicated. So let's do that. So what I'm going to do is I'm going to call this little width B. And I'm going to call this distance here D. But you'll see that this is not very important, because at the end we will just dismiss it. And now I'm going to divide this into two sides. So I'm going to put a separator here at B halves, and I'm going to compare the wave in here with the wave in here. And then we're going to see what happens when they reach a certain point B. Now the first thing that we need to do here, that's a little dirty but works, is realize that if this is very, very big compared to B, then any wave that comes at a certain angle from here will end up at the same point. I know this sounds completely preposterous because of course there's a separation, but I can kind of prove this to you. Now take a certain wave coming out of here at a certain angle theta, and this one is also going out there at a certain angle theta. Now we can calculate the position h of this one by using simply, well, we know this and we know this, and all we need to do is to use the definition of the tangent, right? So we know that the tangent of theta, and because this is so big, so is the hypotenuse, and then the tangent is more or less equal to theta, if theta is in radians. So tangent of theta is more or less equal to theta, and it's going to equal h over d. So h equals d times theta, right? And then this one over here is going to end up at this same height plus b halves, right? But we just said, so the height of this one is h plus b halves. But since h is proportional to d, we have that this is really much smaller than h. So this is more or less equal to h. So they will both end up at the same height. There's another way of seeing it. I'm going to zoom out, and I'm just going to show it to you. So if I zoom out, we're saying that this aperture is actually really small, right? And this is really far away. So what we're saying is, well, for a certain angle theta, whatever is in here will end up here for this angle theta. Now, as you can see, what really matters here is the angle, and it really does not matter what position in the slit you occupy, because this is really small compared to this distance. Basically, what I'm interested in then is the phase difference between any two rays that have the same angle. And now, of course, there's not only these two, right? There's this one and this one, this one and this one, but because the distance will be the same between any two, then the path difference, which is this part over here, will also be the same. And since it's also always the same, I only have to analyze what happens to two of them, and I have the path difference for all of them. So all I need to do is to find out the path difference between these two guys, and then I know the path difference between any two guys that are at the same distance. And all I need to do is then add them up all together. But I don't really care, because all I wanted to know is whether this is going to be a maximum or a minimum. So let's do this. Now all I need to do to calculate the path difference is, well, think about this guy is going to go all the way here, this guy is going to go all the way here. So the difference in their paths will be the fact that this guy starts a little bit earlier, right? So this guy goes for a little longer. So all I need to do is to draw a perpendicular line going like this and figure out this distance over here. So let's do that. Alright, so first thing I do this is a right angle, and so is this one. And then I need to figure out what this angle here is. So let's just draw ourselves a little triangle. And then this, if you know anything about triangles, you'll see that this is theta. If you don't believe me, think about this. This is theta. This is 90. So this is 90 minus theta. So 90 and 90 minus theta plus theta, that's 180. That's a triangle. So if I want to know this little part over here, all I need to do is use trigonometry. I have the sine of theta, and then I have the hypotenuse, which is just b halves. So then I can see that the phase difference is just the hypotenuse times the sine, b halves times sine of theta, and that's it. So that's the phase difference. And now what I want to know is, okay, when is this phase difference going to cause destructive interference? And that's when we go back to interference and we're like, oh, that used to happen when I had two waves like this, and they were separated by half a wavelength. So when this is equal to half a wavelength, then I'm going to have destructive interference. So when b halves of sine of theta equals lambda halves, then I'm going to have destructive interference. And then, of course, I can get rid of these halves, and then I'll get this formula which says that b sine of theta has to equal lambda if I want to find destructive interference. And now I would love to tell you that we're done, but we're not done yet. So bear with me for a little longer. Now, everything that I did before, I could repeat, but instead of dividing my thing in 4, I could divide my slit in 2, I could divide my slit in 4, like I just did here. And then all my argument would apply just the same, but this time the hypotenuse would be b fourths, right? So I would have then the hypotenuse b fourths times sine theta equals lambda half. And then I would still have destructive interference, which means that b sine theta equals 2 lambda. So this would also give me destructive interference. But I could do more, right? So I could, instead of dividing this in 4 pieces, I could divide this in 6 pieces, right? And then I would have b sixths here. So then I would have something like b sixths of sine theta equals lambda halves. And you can see where I'm going. B sine theta equals 3 lambda. So we have b sine theta equals lambda, 2 lambda, 3 lambda, and then I'm sure you can figure out where this is going. We are going to have destructive interference every time that b sine theta equals n lambda, where n is just an integers. And that's what's going to give us the condition for destructive interference. Now, typically, we're only interested in the first minimum. So what we have is really b sine theta equals lambda, because this is the most important one. This is what determines the resolution of our device and whatnot. And because we are normally considering very small angles, then we really can say that b theta equals lambda. Okay, or alternatively, we can say that theta equals lambda over b. Now, if the slit is not rectangular, but it's a circle, things change a little bit, and I'm not going to prove this to you because this would require a large amount of calculus and knowing a lot more about electromagnetism than you do. But you get that theta is actually 1.22 lambda over b. Now, it doesn't really matter. These two are pretty much equivalent. These are approximations anyhow, so either one you use is okay. Just be aware that, you know, if you use a circular slit, you may have to change things a little bit. In practice, you won't tell the difference. We are now ready to talk about resolution. And the thing is, like any optical device is really a diffraction slit, right? So a camera is just an aperture and a screen. And then rays go through the screen and end up here. So these, of course, causes diffraction. What happens is that normally, for the kinds of stuff that we're taking pictures of, the diffraction's not very, visible. However, when we really want a lot of resolution, like when we're using a microscope, then diffraction becomes a real problem. And it actually limits the resolution of our optical devices. And that's one of the reasons that, for example, we use electron microscopes instead of optical microscopes, because electrons have a much lower wavelength than photons, and therefore their diffraction is a lot less, and we can look at things that are way smaller. Now, the thing about diffraction is that when we look at a point, we really don't see a point in the camera, but what we see is a diffraction pattern. So we will see a big point like this. That's our point. And then there will be a diffraction minimum around it, and then there will be a diffraction ring, and actually this goes on and on and on. And this has less and less intensity, but more or less it looks like this, right? And then this goes on. But the main two are these two, okay? The big thing, diffraction minimum, diffraction ring. Now, when you have 1 point, that's all well and good, but what if you have 2? So imagine that you have, so here's my point, and then I'm trying to look at another point that's, I mean, these are real points, like they could be like this small, but they look bigger because of diffraction, because the diffraction maximum is something that goes like this, right? So this is bigger than we would like it to be. And then I could be looking at another point that's very close to it. So let's say that it's here. And the problem is that this point is not going to be a point in my camera. It's not going to be a point here, but it's going to be a diffraction ring. Right? It's going to do something like this. And then, of course, it gets really hard to tell these 2 points apart. And it would be nice if we have some kind of criterion to determine whether 2 points are far enough to be told apart, and when 2 points are so close that because of diffraction they just look like one, there's just no way to know whether there's 1 point there or 2 or what. Now, it turns out that such a criterion exists, and it's called the Rayleigh criterion, and it's a very, very basic one, I mean, common sense pretty much. So all we need to think about is that when we look at a diffraction pattern of a point, it does something like this, right? So this is the maximum, this is the first diffraction minimum, this is the second maximum, and so on. And then let's say that I have another one. So I'm going to duplicate this thing so that we can have our 2 diffraction things. Now, if these 2 things are like that, we're not going to be able to distinguish between these 2 points, because we're actually going to have a blur, right? We're going to have something like this. Okay? So this doesn't work. However, if these things are a little bit further away, let's say this far away, then it may be able to tell them apart. And what Rayleigh said is, well, you know that you can tell them apart when the maximum of your point is at the same position of the first diffraction minimum. So when this happens, you can kind of resolve the 2 points. When this does not happen, when they're further, like when they're closer together than this, then you can't. And it's that simple. Now, we can use this criterion to work out a very general result that will allow us to figure out the resolution of an optical device just by taking a look at the wavelength of the stuff it works with. So we've got, for example, in a microscope, so imagine that we have a microscope and we're looking at something that's in here. Now, hopefully you remember this from the IGCSE, but we put our object at the focal length of our lens. If you don't remember, doesn't matter. The focal length is just the place where the length will make our rays converge. So for example, if you put a magnifying glass in the sun, you'll see the sunrise converging to a point where you can use it to, burn stuff. This length here is the focal length. Okay, so we will normally put this thing at the focal length. And what we want to know is what the minimum resolution that we can observe here is. Okay, and for this we use the Rayleigh criterion that says the 2 points are resolved if the maximum is at the position of the other guy's minimum. And now we know from before that this distance here from the maximum to the first minimum, we could calculate it like that. Remember that it was b sine theta equals lambda, right? And then we basically said that the sine is more or less equal to the angle, so that theta equals lambda over b. And now what I do is, well, okay, let's say that I have 2 points here, point 1, point 2, and they're separated a distance s, and I want to know if I can resolve them, if I can tell them apart in my microscope. Well, then what I can do is say, okay, well, these guys are at a distance f, which is the focal length, and separated by an angle theta. Now, if I know anything about trigonometry, I got that s over f equals theta, right? And I can plug that right in here. So let's do that. So I got that s over f equals lambda over b, and from here I got that S, which is the, well, equals lambda f over b. So this tells me that I can resolve 2 points. This is the minimum distance that these 2 points have to have if I'm to resolve them. It's given by the wavelength times the focal length divided by b, which is the size of the aperture. Now, in order of magnitude, normally this focal length is more or less the same as this b. So what I can do, it's pretty dirty, but I can do this, is just get rid of both and say, look, same order of magnitude, f over b equals 1. So I can say then that S is more or less equal to the wavelength of the light that I'm using. And this is a huge result. So what this is telling me is, how can I know if I can tell 2 points apart? Well, are they more than a wavelength apart? Yes. Well, then I can tell them apart. Are they less than a wavelength apart? Then I can't tell them apart. And this tells me that no matter how good my optical device is, I will not be able to tell 2 points apart if they're closer than a wavelength. And this is huge, because this means that if I want to look at certain things that are very, very small, I can't use regular light, because its wavelength is 480 nanometers. If I want to look at things that are less than 480 nanometers, I can't do that. So I need to use other things. I can use electrons that have a much smaller wavelength. I can use really high energy light, but of course that has a problem. I can burn things, I can destroy the samples that I'm looking at. And of course, if I want to look at something that's really, really, really close together, I'm going to need something with a really small wavelength, which means a lot of energy. And how on earth do I even generate that? So this is a huge result, and it's also a huge problem. And you can interpret the LHC, which is, the particle accelerator at Geneva, just as a giant microscope that's trying to generate particles with a very, very small wavelength so that we can look at things that are very, very, very close together. And the problem is that we need kilometers and kilometers of super cooled magnets in order to do that. Well, that's it for today. I hope you're able to do this, or at least, the formula and know vaguely where it comes from. And I hope that you understood why diffraction is so useful to deduce things about the resolution of optical devices, and why the wavelength of the light that you use is so important. I'll see you tomorrow, and good luck.